In this video, we're going to show that for two positive integers a and b, that a divides b, the GCD of a and b equal 1, and the LCM of a and b equals b are all equivalent. That is, they're all if and only if. So, proof. First, I'm going to show that these two are equivalent. We'll show the GCD of a and b equals a if and only if the LCM of a and b equals b. But this is actually pretty obvious. Recall that the GCD of a and b is ab divided by the LCM of ab. If the GCD of a and b is equal to a, that implies that a, this, is equal to AB over the LCM of AB. Well, then that should be 1. Dividing both sides by 1, we get 1 is equal to B over the LCM of A and B. And there's only one way a fraction is equal to 1, and that's when the denominator equals the numerator. That's what we wanted to show. We started off with this, and we showed that. Now, working backwards is going to be exactly the same. Suppose the LCM of A and B is equal to B. We know that the LCM of A and B, well, that's probably more complicated, but is equal to AB over the GCD of A and B. But this is B. B is equal to A times B over, let me say that the way I really want to say it. I'm rewriting this here as A over GCD of A and B times B. Oh, so what's in the bracket must be 1, because 1 times B really does equal B. So A over the GCD of A and B is equal to 1, which implies the denominator and the numerator are equal. And that is what I wanted to show. So now, these two, this one and this one, are exactly the same statement. Okay, now if I can show this if and only if that one, or A divides B if and only if that one, then they're all three equivalent. Because if this middle one is if and only if the right and if and only if the left, then the left A divides B, and the right LCM of A and B equals B. They too are equivalent. Okay, so I will show that A divides B if and only if the GCD of A and B, say, is A. Okay. So, we go this way. Assume A divides B. That means B is a multiple of A. That implies we're taking the GCD of A and a multiple of A, where M is at least 1. Well, A clearly goes into A, and A goes into MA. Nothing larger than A goes into the first number. Okay, if you have 8, 9 doesn't go into it, 10 doesn't go into it evenly, 11 doesn't. The only prayer that numbers will go into it are numbers less than or equal to 8. Like 1 goes into it, 2 goes into 8, 4 goes into 8, 8 goes into 8. Not every number less than 8 will go into 8, but only numbers less than 8 will go into 8. Okay, so the largest number that goes into A is A, and and A also goes into MA. That implies the GCD of A and MA is A. So I started with this, and I showed that. Now, we go the other way. If and only if proof. Okay, so we assume that the GCD of A and B is 1. Is A. Well, that means there exist X and Y. Let's see if I really want this. Such that there exist X and Y in the integers such that the GCD, which is A, is a linear combination of A and B. But this is going to imply that X is 1 and Y is 0. Because 1 times X plus 0 times Y really does equal to X. But I don't want it to equal X. A times 1. And I have this also wrong. Times B times Y, and I'm saying Y is 0. Well, that does equal A. So, I did find a linear combination, so I'm not so sure that's helping us. Okay. Well, so let me get rid of this as well. Thinking of this just as D, this statement tells us A divides A and A divides B. Okay? But I don't really care about that statement. A divides B. That is, if the GCD of A and B is A, then A divides B. That's what I wanted to show. I wanted to show that if I have this, then I have that. That completes this proof. Nice and quick. All I really did was use definitions. If you like videos like this, definitely subscribe to my channel. Click the like button. Leave a comment, please. I love reading your comments. See you guys in the next video. And don't forget, watch and learn.